Here, I just wanted to know the magnitude of the current I1 in this circuit. So it should be super easy. You should be able to look at it and tell what the answer is. The trick here is to pick the right loop. Right, you have the top loop, the bottom loop, and then the big loop. You want to pick the correct loop that'll make the solution easiest. Alright, maybe not super easy. What loop are you going to pick to find this? The bottom loop? If you use the bottom loop, you have, what is it for? I1? Well, if we use the bottom loop, I1 is not involved in the bottom loop at all. Because the bottom loop has I2 here, and then I3 here. Now, the top loop has I1, right? It's right here, right here. So we have I3 and then I1, and then the big loop also includes I1. So only the top loop and the big loop include I1. Alright, I'm going to stop at 2:45. 10 more seconds. Just guess if you don't know. Alright, very good. Did I tell you all the brown and sticky joke? No, what's brown and sticky? A stick. Okay, what was the answer? 2 amps, right. So I said this one should be really easy. You can just look at this circuit, this branch, this loop of the circuit, and I have 40 volts and 20 ohms. It's just a simple, single loop circuit. And so I say I is V over R. That's 40 over 20, which is equal to 2 amps. Or, really I'd write out my loop rule. I could say go in this direction. I would have plus 40 plus 20 I1 equals 0, and then I1 is equal to negative 2. So I was looking for the magnitude here, so it's just 2. Alright? You might think that this affects the current I1, but it turns out that it doesn't. Alright, let's see. Let's do one of these. This is the equation. Can y'all see these on the board, Christian? You have it in front of you? Okay. Which of these equations is correct, I think? Yeah, which of these is correct? you finish this one, you can go on to the next one. Although I want to make a small change, so not just hold off. Alright, we'll go about 10 more seconds. Let's stop at 205, 205. Let's see, I think A is right. Let's take a look. So I have minus 80 I3. That means I'm starting here and going in this direction. So I get minus 80. It's negative because I'm going with the current. Minus 1 I3. Minus 30. I'm going from high to low, so it's negative. Minus 20 I2. That's correct. And minus 40. And then I come back. So that one is correct. I'm not going to go through all the incorrect ones. Although, let's see. What was the other common one? C was the most answered. 45 I1. Because it's positive, that means I must be going in this direction. But let's see. Yeah, but then I should have a plus 40 here. So, and then a plus 20 I2. So I could make it correct just by making this positive. All right. But you can't change the options. Alright, let's try this one. I'm going to let you do it on your own. I'm going to make it a little bit simpler. Let's take out this resistor right here. So just scratch this resistor doesn't exist. There's just a wire there. Alright. You'll have one like this on your test in a couple of weeks. What, 2 weeks from Wednesday, is that right? Yeah, and a week from Friday, remember there's no class, so. That's right. Yeah, you just pick directions for the currents. I1, I2, and I3.
You just assume that the left one is I1, the middle is I2.
Doesn't matter. That's what I would do, but it doesn't matter. On your test, your system of equations will be pretty simple. This one turns out to be pretty simple to solve. In your homework, it's more complicated. You have three equations, each with 2 unknowns. When I solve this, I'm going to write the left loop, the right loop, and the junction equation. You could do the big loop though if you wanted. But when I do, I'm going to do the left loop and the right loop, and then the junction rule. I'll give you about 4 minutes, then I'm going to jump in there. right equation, right deduction rules, and you want to solve them. Remember on the test, I think you get what, 2 points extra credit for the inversion matrix? Oh, 5, right. I'll give you 5. I think it's worth your effort if you want to try to learn that. Morning. Alright guys, look, I'm going to do my current here. I'll call this I1. I'm going to call this I2. I'm going to have it go down. These are irrelevant for the directions. I'm just picking them randomly. I3. You might have chose different directions for your currents, and that's okay. So your equations will be a little bit different. My left loop, I'm going to start here and go up in this direction. That's 12 minus 2I2, or 2I1 rather. And then I have minus 6 coming down and minus 3I1. That's all equal to 0. On my right loop, let's see, I'll start here and go in this direction. That's minus 4I3. That's it, right? Plus 6 equals 0. Alright, so it's pretty easy. I can solve for I3 right here. I messed up somewhere, didn't I? And then the junction rule is I just pick a junction. Say right here, I have I2 and I3 coming in. And then that's equal to I1. So this is really simple to solve for, right? Because my first two equations, they only have one unknown. Because I didn't have a resistor in that middle branch, choosing my left and right loops made it a very simple system of equations. In fact, you know, might even call it a system of equations. But I can solve this one. I get 12 minus 6, that's 6, minus 5I1 equals to 0. And then I1 is 6/5. 6 divided by 5 amps. It's positive, so I'm going to call it up, or you might call it clockwise, whatever you like, because I1 really goes in this direction. And then similarly, I can solve here. What is I3? Right, 3/2 amps. I'll call it down. It came out positive. And then I solve here. Plug those two into my junction rule. I get I2 equals I1 minus I3. 6/5 minus 3/2. Is that 12/10 minus 6/10? So 6/10, 3/5 of an amp. And it's positive. Looks like I chose all my directions correctly. That's, what is that, I2? So that's down. Alright, if you were doing this by the matrix method, I'm not going to go through all of it, but it would look pretty simple actually. It would be minus 5, 0, 0, negative 6. That's this equation. 0, 0, negative 4, negative 6. That's this equation right here. just written in terms of I1 plus I2 plus I3 equals whatever your constant is. And then negative 1, 1, 1, 0. That's this equation right here. And then you'll go and find the identity matrix using those rules that we did. There are only a couple steps here. You divide this one by negative 5, divide this one by negative 4, and then you would subtract this one from this one, right? To get rid of this one, and then subtract this one from this row. Using those negatives. Alright? Okay. In the homework, I think I go through this as well if you want to practice this. Or you can look online. There's all sorts of practice problems. Y'all got a multi-loops? It will definitely be on the test in 2 weeks, so. Alright. Alright. Let's do a few more clicker questions. Oh wait, have we done these? Okay, I might have seen the answer, sorry. Alright, what happens to the voltage across the resistor R1 when the switch here is closed? So if I take the switch and I close it, that's I'm adding R2. What happens to the voltage across R1? Does it increase, decrease, or stay the same? Alright, I'll stop at 50. Alright, I'm going to start it again. I'm going to explain. Everybody was split. A couple of you didn't split, but most of you were split between A and B. One of those is the right answer, but one of them's not, obviously. What happens when I close this switch? What happens to the equivalent resistance of this branch? Does it go up or down? It goes down. Remember when I add resistors in parallel, my equivalent decreases. I'm adding more paths for the electricity to flow. So if I close this, my equivalent resistance of this goes down. Now voltage and resistance are linearly related, right? Are directly related. If resistance goes up, voltage goes up. If resistance goes down, voltage goes down. So if this resistance decreases, the voltage will also decrease. Now what's going to happen to the voltage across R1? I'm going to stop about 105. Y'all are still pretty evenly split between A and B. Ask your neighbor what they put, please. Or maybe ask another neighbor. Alright, look folks, if this voltage across this whole thing goes down, what's going to happen to this voltage? It's going to go up, right? Oh no, y'all were good, I'm sorry, y'all were going in the right direction. Okay, what's the answer? You don't know anymore. Alright, look, this voltage is going to go down because this resistance decreases. So this voltage, if this voltage goes down, you know, they have to add up to equal this. What's going to happen here? It's going to go up, right? So A is the right answer. What happens to the voltage across resistor R4 when the switch is closed? If I add in this resistor R2, what's going to happen to R4? The voltage across R4. Alright, very good. Doing well. right, I'll stop at 40. B is the right answer. Very good. What is Mozart doing right now? Decomposing. Okay. Just like we had before, we add that resistor, the equivalent decreases, so the voltage across all those resistors decreases. Which resistor has the greater current going through it? If all these are equal, which one has the greatest current going through it? If our current splits up at each of these junctions, so I have a current coming off, it splits up here, and then it splits up again here. I want to know which one has the greatest current. If all these resistors are equal, what's going to happen to the current here? How is it going to split between R1 and R2? They'll be split in half. So I get equal currents here and here. It doesn't happen here though, because I have different resistances. I have a bigger resistance here than I do down here by a factor of 2. So my currents will be different here. Let me repeat what I just said. So here, I get half the current through each of these, right? The sum of the currents, like the sum of the currents here and the sum of the currents here, they have to all equal to the current that's going through the main part of the circuit, right? I get half the current here and half the current here. Over here, I get a certain amount of current here and a certain amount of current here. And the total of those two currents has to equal the same amount that was going through that first current, right? So I want to know now which of these resistors has the most current. You know, a lot of you are putting B right now, R1 and R2 equally, right? They have equal amounts of current, but they don't have the most amount of current. So B isn't the right answer. Let's just get rid of that. They don't have the most current. Either R1, R3, and R4, or R5. It's not B either. All right, I'm going to stop at 210. Which one do you think it is? D is right. Right. Because here, I have a really big resistance. So let's say I'm at 3 amps, right? 3 amps, I get 1.5 amps, 1.5 amps here. Okay? Here, that 3 amps comes here, and it says, oh, where am I going to go? And it says, well, this is like a tough road. I'm not going to go this way because it has a lot of resistance. So I'm going to get 2 amps that come down here, and just 1 amp that comes up here. If my resistance goes up, my current goes down. Because, you know, it's the tough road to go. So you want to go the path of least resistance, as they say. So D is right. Expect some questions like this on the test. You're sort of looking at a circuit and what happens when you add resistors, or just qualitatively, what are the currents and the voltages. All right, what is the... Oh, such a pain in the butt. What is the current in branch P? I have 5 amps here, 8 amps coming here, so I know what is this current. All right, I'll stop about 35 or so. Go on to 40. That's everybody. Okay, good. D is the right answer. If I have 8 amps coming here, right, this is a junction of 8 amps coming here, I lose 2 amps here, so I have to have 6 amps here. 6 plus 2 equals 8. What's my current here? 3 amps, right. We're going to skip this one. Y'all doing this in lab, but what is the current through an ammeter here? If I have a Wheatstone bridge, I'm not going to put it up, but if I have a Wheatstone bridge and I have equal resistors all the way around, you got done Wheatstone bridge yet? Yeah, I have 0 current here. This is how it used to. They use these to measure unknown resistances. They would have a box, just a bunch of resistors, and you would compare one resistor to another. I mean, now we have multimeters, and they work a lot better. But you would have this big box. We used to have one. And you just hook up your resistor, and then you find the right comparative resistor to make it so that you have 0 current through here. All right? And I think this is the last one. Which one of these is correct? Which one of these equations is correct? Looks like I got this down pretty well. Let's do about 10 more seconds, 120. Just guess if you don't know. I go C is the right answer. 2 minus I1 minus 4 minus 2I2, I'm starting here. Right, plus 2 minus 1 I1 minus 4 because I'm going from high to low potential minus 2I2 equals 0. And all these others are wrong for various reasons. They have the wrong sign, they're missing a current, they have the wrong current, whatever. But C is the right answer here. All right, folks, let's go on to RC circuits. So we really just sort of have 2 more small topics on this. We'll probably wrap this up on Wednesday, this whole chapter, and move on to magnetic fields in the next chapter. So we're going to look at RC circuits. We're not going to get much into it, honestly, just sort of a couple of basic things. In circuits with capacitors, the current varies with time. In fact, you know, one of the purposes of capacitors is to store energy. Another one of the purposes of capacitors is to have very regularly timed circuits. So, for example, if you have a flashing light, you can use a capacitor to have that light flash on and off at a very regular rate, because capacitors will charge and discharge at a very regular rate in a particular amount of time. So if you have like a flashing hazard light or whatever, that can be, and often is, just a couple of capacitors that are used to charge and discharge at this regular rate. So after you turn a circuit on, the capacitor charges. So if you have a circuit like this, when you close this switch, electrons will go through the resistor and then they'll populate the plates of this capacitor until it's fully charged. When it's fully charged, you no longer have any current. I'll show you a graph on the current here in just a second, but when you first close that switch, this is our current, this is our time. When you first close it, you have a big current, and then as time goes along, as you fill the charge of that capacitor, as the charge increases, then our current goes to 0. So if we were to plot actually our Q, initially our Q would be small, it would have 0 charge. This is Q on the capacitor, but then it gradually gets bigger. And as that charge on the capacitor gets bigger and bigger, the current that's going through the resistor into the circuit gets smaller and smaller. So our current changes until our capacitor is fully charged. When that capacitor is charged, the charge is C times V. Right, we've already seen that. And this charge is an exponential function. Right, y'all seen these functions before, probably. Right, exponential functions. Yes. Our charge then is equal to our maximum charge times 1 minus e to the minus t over RC. And similarly, our current is our maximum current times just e to the minus t over RC. Our maximum charge again is CV, so it's CV times 1 minus e to the minus t over RC. And our maximum current is V over R, just from Ohm's law. Both of these are on your equation sheet, these expressions, and you could have a simple problem just asking, as you're charging a capacitor, what is the time, or excuse me, what is the charge or the current at a particular time? By the way, if I also plotted my voltage would look the same as the current here. I would start out at a big voltage, and then that voltage would gradually decrease. Same function as the current. There's those functions. This is our current. As I said, it's also our voltage, and that's our charge. Remember the maximum here. This is V over R. I equal V over R. And then this charge is C times V. Q equals C times V. Alright, so that's charging a capacitor, and then after you charge it, you can discharge the capacitor, you can remove the battery, and then the charge can be used at a later time. So it would look like this, where I just have a capacitor and a resistor. You'll remember the video that we watched, the Make Zine video with Colin Firth, I think, no, not Firth, he's an actor, isn't he? Colin Cunningham, that was his name. He took a 9-volt battery and he charged a capacitor, and then what did he use the capacitor for? Do you remember this? No, that's something different. Did we watch that video? I'm pretty sure we did. Huh? Yeah, it's sort of long here. Right. He built a capacitor out of a film canister, and then later in that video, he actually took a capacitor, charged it with a 9-volt battery, and then he used that capacitor to light up an LED. So he charged it first, and then he discharged it. It brightened and then it dimmed. So this would be discharging. This would be like what he did with the capacitor through the LED. So here, our current voltage and charge, they all decrease with time. So if I were to plot this, my charge, the current, and voltage, they all sort of start with a maximum value, and then they decrease. And so they all follow this function. Our Q max, e to the minus t over RC. I is I max, that's V over R, e to the minus t over RC. And then V is just the V of the battery, e to the minus t over RC. There is no battery here, but whatever voltage you had on your battery, that's the voltage that you'll have on your capacitor. Because you put that maximum charge on it, and then that capacitor now holds that voltage, and you can use it for later. Alright, let's, oh, and then we also characterize these RC circuits. So be prepared to use any of these functions to find the charge or the voltage. I think we'll do a practice problem here in just a second. Do y'all know how to use the exponential function on your calculator? Have y'all used it before? Yeah, it's usually second natural log. We'll practice it in just a bit. We also describe the time for charging or discharging a capacitor by the time constant. We call this tau, not to be confused with twice pi. This is something different. All right, time constant tau is R times C. It's not the time for the capacitor to discharge or charge, but it characterizes that time. Like it did some multiple of that time in this exponential function. So it is a time, and the units are in seconds, of course. And after 10 times the time constant, then the capacitor is almost 100% charged or discharged. So if I'm looking at, say, the charge versus time for when it's charging, it looks something like this. At this time, that time is roughly equal to 10 tau. So, tau is my time constant, is right over here. But at 10 times that time constant, is basically fully charged or discharged. It's never actually completely charged or discharged because it's an exponential function, right? Exponential functions approach some value and but they never reach it, right? But at this point, it's like almost 100% charged. All right, let's try this quick problem. Remember, mega is 10 to the 6, micro is 10 to the minus 6, that you've forgotten. Don't try to make this more complicated than it is. Here we just want to know the total time required to discharge. So in the course of that, we'll need to find the time constant and then do what with the time constant. Oh, n is mega, is 10 to the 6. The time required to discharge is what? In regards to the time constant. 10 times the time. Alright folks, we're sort of all over the board here. I'm just going to help you with it. So here, our tau is equal to R times C. We just want to find the time constant. Remember that time constant, it characterizes how long the capacitor takes to charge or discharge. That's 1 mega ohm times 4 microfarads. Often in RC circuits, you'll have a really big resistor which limits the current, and then a really small capacitor. So get used to these. Mega is 10 to the 6. Micro is 10 to the minus 6. These cancel out then, 10 to the 6 times 10 to the minus 6. So this is just equal to 4 seconds. And so the total time required then is what? 40, right. So it takes 10 tau. So it's not 4, but it's 40. A lot of you put 8. I'm not sure why you put 8, unless you just multiply the numbers. I know that often students, they don't know the answer, they just multiply all the numbers together. Y'all do that? Because often I put that as an answer, and a lot of students give it. But in this case, the 2 volts is irrelevant. You don't need that at all. Okay? Yeah, good. So 10 is, or A is the right answer. Got 100%, but no joke. That helped you a lot. Wait, hold on. I think, was there one more? Oh, let's see. We're going to skip this one. And I want to just go ahead and set this one up. We have a couple minutes left. Okay, I know that y'all are ready to go. So here I want to first ask, after 5 seconds after closing the switch, that's after closing this switch, what is the charge on that capacitor? So I'm really only considering this part of the circuit for the first part because the top part's not even open. So after 5 seconds after closing the switch, if I want to know the charge, it's going to equal to Q max times 1 minus e to the minus t over RC. And this is going to be equal to C times V times 1 minus e to the minus 5 over, I'm going to calculate my tau over here. It's going to be 2 ohms times 1 farad. That's equal to 2 seconds. So negative 5 over 2. All right, C is 1 farad. I have 6 volts here. 1 minus e to the minus 2.5. And we'll come back to this. We'll fill this in next time. All right. Make sure you're up on your exponential functions, but we'll try it next time.